All right, we're now about to move into understanding pointers in Go, and this is really critical for our ability to understand the cost and the engineering decisions that we're making. And there's a lot of things I want to cover in this section, including how memory works and the ideas of value and pointer semantics. We're going to cover all of that, but initially what I want to do is get into that first code review. So I'm going to bring in our pass by value. And when we talk about pass by value, what we really mean is that everything in Go is about making a copy of data as we transition across these program boundaries. Now, I've got a piece of code up here, and it looks fairly simple. If you've been programming for a couple of years, there's nothing necessarily novel going on here. But you wouldn't imagine how much actually is happening behind the scenes. And I want to touch upon some of that as we go. And to be able to do that, we've got to have a small conversation about the scheduler. Not a complete conversation, just enough to make sure that we have an understanding of how these pointers and pass by value and the different semantics, pointer and value semantics work. Now, before we even get into this code, one of the things I want to do is show you what my machine looks like here. So I'm going to click on that apple. I'm going to say about this Mac. And once that comes up, I'm going to be doing a system report. And I'm going to zoom in to this area right here. And one of the things you're going to see is that this machine right now is running an Intel i7. It's running at about 3 gigahertz. All right, that's a 3 gigahertz processor. I mean, it can run a little slow. It can boost depending on temperature. And it's got one physical processor with 4 cores. Now, Phil, why are you telling me all this? Well, let's talk a little bit about what happens when your Go program starts up. When your Go program starts up, what the runtime is going to do is look to see how many logical processors or cores you have on your machine. And the way we do that is to look at how many physical processors we have. I showed you we have 1. How many physical cores we have 4. But since this is an i7, we end up with 2 hardware threads per physical core. And a hardware thread is what we use to execute an operating system thread. So on this hardware that I'm going to be running on throughout this series, we literally can run 8 Go routines, or 8 paths of execution in parallel at the same time. 1 Go routine per hardware thread, 2 hardware threads per physical core, and 4 physical cores per processor. So what's going to happen is when this Go program starts up, and on the playground, from the playground's perspective, all we have is 1 physical core with only 1 hardware thread. So it's a single-threaded environment, right? 1 Go routine. What's going to happen is the runtime is going to create what we call a P. And that P is going to stand for a logical processor. So on my machine, we're going to have 8 of these. On the playground, we're only going to have 1. And that P is going to be attached to something that we call an M. And that M stands for machine, and it represents a real live operating system thread. We're going to talk much more later on in this series how all of this stuff is connected. But that M is still going to be scheduled by the operating system to run on some hardware thread in order to do some work. So we're going to be a layer above the hardware, leveraging that M. That M is going to be scheduled by the operating system to run on our hardware. On the playground, this is all we have. Our hardware is a single-threaded environment like this. Again, on my machine, there's 8. And we get one more thing, which is a Go routine. And that Go routine is equivalent to the M. So we think about the M, or machine, as an operating system thread whose job it is to execute instructions sequentially, one after the other, leveraging the hardware. And our Go routine is very similar to an M. We're going to learn this stuff again later, where it's an application level thread. Here's our operating system level thread. This is our application level thread. It behaves very similar. Its job is to execute the instructions we're writing sequentially, one after the other, but it leverages the M to do that, just like the M leverages the hardware to do that. We're this layer of indirection. And really why I'm bringing this up, because I want to talk about memory. And one of the things that we have here is a piece of memory we call the stack. Now, every Go routine gets its own contiguous block of memory for its stack, and it starts out at 2K. Operating system threads also get a stack. Now, stacks work differently depending upon the operating system that you're using. Kind of as an example, if you were running on Windows, Windows can allocate a full meg of memory for the stack for that operating system thread out of the box. Boom, 1 meg of memory. I mean, it's a lot of memory allocation for potentially not even using the bulk of it. Linux is a little bit better. It will allocate a stack, initial stacks based on operating system page size, and if it needs more memory, it will grow. And Go goes after the same idea, but we go with a very small initial stack of 2K. I mean, compare 1 meg to 2K. And this can grow as well, as we'll talk about. And the idea here in Go is not only to have high levels of integrity in everything we do. It's also about minimizing the amount of resources, like memory, that we're using at any given time, because Go knows that the software we build today runs on cloud machines, right? On that shared hardware, shared server stuff. So we've got to really be smart about minimizing the amount of resources we're using at any time, just to manage cost and to be able to leverage more hardware with more software. And so the idea is that, you know, maybe we want to have 50,000 Go routines running at any given time, if it's reasonable and practical to do so. With a 2K stack, we could pull that off. With a 1 meg stack, not going to happen. So this is really what I want to show you right now. We're going to go deeper in how all this stuff works later, but right now what I want to do is share the idea that we have this 2K stack. So I've got 50,000 Go routines, I've got 50,000 stacks, and they're all here. And that's what's important right now. What's important right now is to understand that when this Go program starts up, we're going to have that P, we're going to have the M, we're going to have our G. That G is going to get this stack, and this program is going to want to start executing. Now, right when the program starts, this Go routine that we're getting is going to be executing some code originally around the runtime. And we're going to get this stack. Now, here's the cool part, okay? Here's our stack right here. Our Go routine is doing some work. And now what that Go routine wants to do is come in and execute the main function. So we see the main function right here on line 7. And one of the things we want to understand is every time a Go routine wants to execute a function, we want to consider this moving across a program boundary. We're about to go from one program boundary to the next. And every time a Go routine crosses over a program boundary, what we're going to do is that Go routine is going to take a slice of memory off the stack, and we're going to call this slice of memory right here a frame. So this frame is a sandbox. The Go routine is now locked into this sandbox. Essentially, the only memory that this Go routine can read and or write is right in here. And by putting the Go routine in timeout, we're really protecting the integrity of our program, because if there's going to be any modification, we don't care about reads. Reads are simple. Reads are easy. It's the modification, right? It's that modify operation, that write operation, which causes us our bugs. And by locking this Go routine right in here, any mutation that it performs on state is here, and it can't be widespread, right? So we're locking the Go routine into this box. If the Go routine is now going to move from this function to another function, then we're going to move. So here's the other thing, right? Every function, think about this for a second. Every function is essentially a data transformation, and every data transformation is input, manipulate, output. However that all comes in or out, we'll talk about API design later. And in this function right here named main, the input is being generated internally. So if you go back and look at this code right now on line 10, we're declaring a variable named count using our short variable declaration operator, assigning it to 10. That's going to be an integer. And that's our input for this function. It's not being passed in. It's being generated internally. And that's OK. There it is. And so since the Go routine is only operating within the scope of this frame, the input has to be in here as well. So now the input for this function is sitting right here inside the frame for the variable count. When you see a variable all by itself there on line 13, I've highlighted count there, then what you're saying is the value of count, what's in the box. When we use that ampersand operator against the variable, now what we're saying is the address of count. Where is the box, right? And this is an operator that lots of languages use, Go's not being novel. So this brings you to the point that moving forward, you're going to hear me say 3 words. You're going to hear me either say value, I mean what's in the box, that integer. You might hear me say address, that's the location of the box. And sometimes you might hear me say data. And when I say data, I mean both the value and the address, because really as programs go, we're either working with the value itself or the address or location of that value. And if you hear me say data, I'm talking about both. There are times where both become important. Now, what's really more interesting here is on line 16, because on line 16, we're about to make a function call, which means we're about to cross over a new program boundary. So when we call line 16 and we call increment, several things are going to happen. We're going to have to create a new frame or box. The Go routine is going to have to move into this new sandbox right here. And since this is now the only memory that the Go routine can operate against, that means, again, it has to get its input. It can either be passed in, it can be generated, or it could kind of find its way in maybe through read calls or things like that. And in this particular case, if you look on line 24, what we see is that the input is passed in. It's very explicit. I love function parameters because they're very easy to read, right? It's very explicit. In order for this data transformation to be able to be performed, the Go routine needs this integer, and it's got to come in from the outside as we cross over this program boundary. And that's exactly what's happening on line 16. So if you look on line 16, you can see the function call is happening, and you can see that the variable count is part of the function call. And what that says is make a copy of the value that's inside that box for count, which is an integer. And if we're going to make a copy of that integer value and we're going to pass it across the program boundary, we need a place to store it. And mechanically, this is what parameters are for. We're going to talk about API design, and we're going to do these things, but parameters are really a mechanic for getting that input inside that sandbox, right? Inside that frame in order for the data transformation to be performed. And so what we say here is make a copy of that integer value and let's operate on our own copy. And that's now what's happening right here. When we get inside this increment function, the Go routine is now operating on its own copy of that integer. Now, this is beautiful because anything this Go routine does in terms of modifying this value is on its own. It doesn't affect any other part of the program. This is the safest way, right, to work with data. And this is what we're starting to talk about, our value semantics. Anytime a function is going to operate on its own copy of the data, we're going to call this value semantics, the safest way to work with data in our programs. Now, what's interesting really is on line 27. Because on line 27, you have the inc++ operation. And that's a read, modify, write operation. What really makes it interesting is the write operation. Because now what's happening is that Go routine is going to come in here, and it's going to modify its own value, right? It just went from 10 to 11. But remember, that modification is in isolation. It's isolated here, only within the scope of this frame in this sandbox. That modification can't affect any other part of the program but this one. And then what you end up seeing is we display the value of and the address of this inc value. That's great. And if I run that program, you can see a couple of things from the output. One thing I want you to notice is that the address of the count variable is at A7AC. So this was at A7AC. We could just look at the last 4 digits. That would be enough. Yet the next variable, right, the inc inside that frame below us is at A7A0. A7A0, lower in memory. We're moving down the stack every frame, lower in memory. We should see that, right? The implementation itself is not as important. I want you to just notice that we were transitioning into these different frames. You see that through the address. But what I also want you to notice is once we're done printing this information, this Go routine returns out of this function, which takes this Go routine out of this frame and moves the Go routine into this frame. And now what is interesting is that when we display the value of count, it's still 10. Remember, the modification happened here in isolation. It doesn't affect the rest of the program. We move back up the call stack. We're back where we were. So we call this value semantics. And the idea of value semantics is every single function, in this case, right, gets its own copy of the data. This is the safest way to work with data. Again, I'm not going to focus so much on reading, but on the modification of data. Because if we do something wrong on the right, and then we're able to move back up, well, that doesn't affect us anymore, right? And a lot of wonderful things happen with our value semantics. I'm going to show you when we get to multi-threaded software development that we're going to get some better performance out of data locality. We're going to be more sympathetic with the hardware in many cases. Like, there's huge, huge benefits. But like I said, nothing is free. And when we talk about nothing being free, it's the same with value semantics. So what is the cost of value semantics? Well, the cost of value semantics is inefficiency. There's a lot of inefficiency with these value semantics, and sometimes that inefficiency creates so much code complexity that we're not able to use it. Now, what do I mean by inefficiency? Let's say that I had 4 people that I wanted to give data to. So I give this person a copy, this person a copy, this person a copy, and that person a copy. Now let's say these people are modifying the data by themselves, which is totally fair. But now I want a clear picture of what the data looks like. I've got to reassemble all of these copies into kind of one view. That's a lot of complexity. So a lot of times, if we're in a situation where it's not efficient to give everybody their own copy because there's modifications going on, then our value semantics don't work. Even with all the beautiful benefits of it, sometimes the inefficiency of it makes it not really reasonable to use. So now, what is the opposite of value semantics? Well, the opposite of value semantics is pointer semantics. This is where pointers come in. And what pointers do is allow us to share a value across a program boundary. So instead of every single function getting its own copy, and we have that beautiful isolation around mutation, now what we're going to do is share the one version of the data across these program boundaries. We're going to gain a lot of efficiency. Now, if I share the value with these 4 people and they modify it, well, guess what? I don't have to worry about reassembling it. I'm seeing those modifications as they happen. But there's a big cost to these pointer semantics. We call them side effects. And it's why programming languages like functional programming languages are trying to get rid of pointers, because these side effects can cause bugs. And a lot of times the nasty bugs we have around data mutation is due to these side effects. So why don't we take a look at a piece of code here that shows these pointer semantics.